Engineers are one of the smartest people on the planet. They design rockets that land themselves, build algorithms that recognize faces, create systems that process billions of transactions per second. But here's the thing that will blow your mind. Intelligence doesn't make engineers better decision makers. In fact, it often makes them worse. The same cognitive abilities that help you debug complex code and design elegant architectures are systematically sabotaging your judgment. The worst part? The smarter you are, the more vulnerable you become. Today, I'm going to show you exactly why this happens and, more importantly, what you can actually do about it. First, let's talk about what cognitive bias actually means. Think about last time you drove the familiar route, say from house to your grocery store. You probably don't remember making most of the turns, checking your mirrors, and deciding when to brake. Your brain automated the entire process. This automation is incredibly efficient. If you had to consciously think about every driving decision, red light ahead, foot pressure on the brake pedal, check mirrors, calculate stopping distance, you will never make it out from the driveway. Think your early days when you were learning how to drive. Your brain works the same way with thinking. Psychologist Daniel Kahneman calls this System 1, fast, automatic, intuitive pattern matching. Most of the time, it works brilliantly. But sometimes these mental shortcuts lead us astray in predictable ways. That's cognitive bias. And here's the kicker. Every human who has the brain is biased. Period. That's not the bug of human cognition. It's a feature. These shortcuts help our ancestors survive, and they're hardwired into how we process information. Now, if you're an engineer, you're probably thinking, okay, if I know I'm biased, I can account for it and control it. That's how engineering system works. Identify the problem, quantify it, build a solution. But that's exactly the trap that makes smart engineers make stupid decisions. Knowing about cognitive bias doesn't fix it. It's like knowing you have a habit of checking your phone too much. Awareness doesn't automatically change the behavior because the habit runs deeper in conscious thought. It's automatic, hardwired, faster than your rational mind. But instead of habits, you cannot think your way out of cognitive bias. You are biased, period. Let me show you what happens when they compound in complex systems, like engineering teams. In 2018 and 2019, two Boeing 737 MAX aircraft crashed, killing 346 people. The immediate cause was a software system called MCIS. But the real story is how multiple cognitive biases cascade through one of the world's most sophisticated engineering organizations. It started with anchoring bias. Boeing's engineers anchored on an existing 737 design instead of crafting new aircraft. Why? Because pilots will need retraining, and that will be cheaper for airlines. This first decision locked in all subsequent choices. Then confirmation bias kicked in. When early test data suggested MCIS might be dangerous, engineers focused on the data that supported the existing design rather than investigating the warnings. They had already committed to the approach. Overconfidence bias made it worse. Boeing's engineers had decades of success. They assumed they could handle any complexity that arose. So they have made MCIS more aggressive and gave it control authority they never would have accepted in a new design. Finally, sunk cost fallacy sealed the deal. By the time the serious problem emerged, Boeing had invested billions in development and taken thousands of orders. Admitting that design was fundamentally flawed would have cost more than continuing with the known risks. 4 cognitive biases cascading through the system built by some smartest engineers in aerospace. The result? 346 deaths and 20 billion crises. This isn't about bad engineers making bad choices. This is about how human cognition works when the smart people face complex, high-pressure decisions. So let me introduce Alex. Senior software engineer, computer science degree, 8 years of experience. The person everyone goes when things break. Alex is brilliant. Alex is also about to make 9 stupid decisions. But first, let me give you a challenge. As I go through these 9 biases, count how many you recognize from your own team or recent project. I will guess how many you have at the end of the video. Bias number 1. Planning fallacy. Alex gets assigned a new feature. Add user authentication to the company's internal tool. How long will it take? Asks the project manager. Alex thinks, I've built login systems before, there are plenty of libraries for this, the requirement seems straightforward. 2 weeks. Alex says confidently. 6 weeks later, Alex is still dealing with password reset flows, account locking policies, integration with the company existing user directory, and that weird edge cases where users have apostrophes in their email addresses. None of this was in the original simple login request. This is a planning fallacy. And here why it happens. When we estimate future tasks, our brain automatically focuses on the best case scenario. We think about the main path, happy case, the part we understand. Our minds literally cannot simulate all the complexity we haven't encountered yet. Looking in the past, we underestimate how long this thing took in the past. It's not the pure planning, it's how human prediction works. We systematically ignore what we don't know. Bias number 2. Confirmation bias. Alex's authentication system is live, but its users are reporting intermediate login failures. Alex investigates and finds that 99.2% of logins succeed. This must be a user error, Alex concludes. Alex spends days optimizing the happy path, making successful logins even faster. Meanwhile, the 0.8% failure rate is caused by the timing issue that only happens when the database is under load. Alex never investigates because the data confirms that the system is working fine. The confirmation bias makes us search for evidence that supports what we already believe, while ignoring contradictory information. Alex unconsciously filters reality to maintain confidence in the design. Bias 3. Anchoring event. New project. The team needs to send real-time notification to users. Alex first thought, we need WebSocket to real-time communication. The team discusses alternatives, maybe simple email notification or push notification, or even just updating the page when users refresh. But Alex keeps comparing everything to the WebSocket solution. Sure, email will work, but what if users want instant notifications? The fact that users never actually ask for instant notification becomes irrelevant. They built WebSocket solution. It works, but it's way more complex than needed, and most users check their notification only once a day. That anchoring effect made Alex's first technical idea win, regardless of whether it matched the actual user needs. Bias 4. Overconfidence bias. It's review time. Alex is checking a teammate solution for handling customer data exports. Alex quickly scans through the code and looks good, follows the patterns, handles the main cases. Looks good for me, says Alex, and approves it. Alex missed something obvious. The solution doesn't handle what happened when customer requests export data for 50,000 records instead of usual 50. In production, this creates massive files that crash the browser and aggregate support tickets. Expertise created overconfidence, which led to less careful checking, not more. Bias 5. Sunk cost fallacy. 3 months into the notification project, it's clear that WebSocket approach is causing problems. Connection drops, scaling issues, battery drain on mobile devices. A colleague suggests switching to simple push notification, a solution that would solve most of the problems. Alex resists. We've already built all real-time infrastructure, the connection management, the heartbeat system, the reconnection logic. Starting over would waste 3 months of work. So they continue WebSockets. spending 2 more months building workarounds for fundamental architecture problems. The sunk cost fallacy made Alex continue a failing approach because accepting that previous work should be abandoned felt too painful. Bias 6. Availability heuristic. Alex is building a file upload feature. Alex focuses on common cases, small images, good network connection, supported file types. Security review comes up and someone asks about handling malicious files. How often users actually upload malware? Alex thinks. Alex has never personally seen a malware upload attack. The colleague mentions some theoretical scenarios, but Alex has no vivid memories of such incidents, so they feel very unlikely. Alex implements basic file checking, but skips the expensive virus scanning. 6 months later, a sophisticated attack uploads malicious files that bypass their simple violation. The availability heuristic made Alex underestimate low probability but high impact risks because there were no personal evidence that made them feel real. Bias 7. Dunning-Kruger effect. New technology alert. The team is adopting Kubernetes. Alex reads the documentation, watches some tutorials, successfully deploys a test application. This is pretty straightforward, Alex thinks. Just containers with some orchestration. Alex volunteers to design the production setup. Alex confidently proposed a complex architecture with multiple environments and custom configurations. The operations team raised concerns about the complexity, but Alex dismissed them. Once you understand the concept, it's not that complicated. 3 months later, the production system is a nightmare of broken deployments, configuration issues, and mysterious outages. Alex's initial competence made Alex overestimate expertise in the domain that he barely understood. Bias 8. Curse of knowledge. Alex presenting new API design to the production team. Alex starts with, so we've implemented REST architecture with token-based authentication, rate limiting through caching and async processes through the background jobs. Blank stares from product managers. But Alex continued. The input follows the HTTP methods, we've got proper error responses, and the data format used JSON with consistent field naming. More blank stares. This is basic API design, don't you understand? The curse of knowledge makes it impossible to Alex to remember what it's like to not know what he knows. Alex's deep technical expertise makes communication with people who don't share the same background nearly impossible. Bias 9. Illusion of transparency. Team stand up. Alex says, authentication integration is done, just need to handle some edge cases. Alex is confident everyone understands what this means. Teammate Sora thinks Alex means testing with different browsers. The product manager thinks Alex means handling users who forgot their passwords. The QA engineer thinks Alex means testing with slow network connections. Nobody asks for clarification because Alex seems confident, and they all think they understand. 2 weeks later, they discover Alex meant none of these things. Alex was thinking about integrating with company existing user directory, something nobody else knew was required. Alex overestimated how clearly the message was communicated, while teammates overestimated how well they understood. Before we move to solution, let's pause. Go ahead and leave a comment mentioning number of biases you counted. If you have less than 3, you're lying. So, 6 months later, Alex attends a conference session about cognitive biases engineering. Alex learned all these 9 biases I just described. Finally, Alex thinks, now that I know about this, I can avoid them. Next week, Alex gets a new project, implement a caching system. 1 week, he says confidently. Planning fallacy strikes again. Alex immediately thinks about Redis because it's a familiar solution. When early performance tests show mixed results, Alex focuses on the metrics that make Redis look great. Confirmation bias in action. Knowing about cognitive biases didn't help Alex at all. If anything, it just made Alex more confident in immunity to these effects. So here's uncomfortable truth. You cannot debug your own brain. These biases aren't bugs in your thinking, they are features. They are automatic, unconscious, faster than your rational mind. They help humans survive for thousands of years, and they are not going away. You're going to be biased tomorrow, next week, and for your rest of your career. So, if we can't fix our brains, is there a way to make better decisions? Actually, yes. But solution is not in you, it's in your environment. The solution isn't to become less biased, it's to build systems and processes around your work that breaks automatic actions and force you to use system 2, the second part of your brain that is logical. The one you can't control. The same systematic thinking that makes you good at engineering can be applied to engineering decision making itself. Instead of relying on individual awareness, we build systems that account for predictable human cognitive failures. But what does it mean in practice? Here are some systematic approaches that you can implement starting tomorrow. So first is what could go wrong sessions for planning fallacy. Before starting any project, spend 20 minutes listing specific ways it could fail or take longer than expected. When Alex started doing this, project estimates become much more accurate. Second is devil's advocate for confirmation bias. In every major decision, assign someone to argue with the opposite view. Make it their job to find problems with the current approach. Its role, not a personality trait. 3. Three options rule for anchoring a fact. Before committing to any technical approach, force yourself to evaluate at least 2 alternatives using the same criteria. The act of comparison breaks the anchor of your first idea. Document them along with chosen solutions so you can refer them back in the future. 4. Systematic checklists for overconfidence bias. Create specific verification steps for common review scenarios. Don't rely on general expertise. Use systematic verification. Does it handle timeouts, large datasets, authentication failures? Create checklists with all of those questions. Timebox experiment for sunk cost fallacy. When you are exploring any approach, set a hard deadline for making work. If you can't solve fundamental problem in the time box, you abandon the approach regardless of previous investments. Disaster brainstorms for availability heuristic. Regularly imagine low probability, high impact scenarios. Make it systematic, not ad hoc. What would happen if this service goes down? What if we have 100x normal traffic? If someone uploads a massive file? Imagine all of those scenarios. Learning check session for Dunning-Kruger effect. Before making any major decision in a domain that you are new to, spend time with someone who has a deep experience in that area. Not to get an approval, but to identify what you don't know you don't know. Next one is explain like I'm 5 years old for curse of knowledge. For any complex technical decision, write an explanation that kid would understand. If you can't explain it simply, you probably don't understand the implication yourself. Mandatory questions for illusion of transparency. End every technical discussion by asking what question do you have and wait for real answers. Don't accept makes sense or sounds good as confirmation of understanding. Make sure that there actually are questions to what you said. The best engineers aren't the ones who avoid cognitive bias. They're the ones who build systems that work despite it. I hope you enjoyed this video. Make sure to subscribe to learn more about engineering and see you in the next video. Bye!